This video is a step-by-step solution for the example entitled Stirring Water at Constant Volume. In this example, you will learn about analyzing the process of stirring water in a closed, rigid, and well-insulated tank and applying the energy balance for a closed system to evaluate the change in temperature in the tank and in mechanical work needed to stir the water. Let's look at the problem statement as given to us. A well-insulated rigid tank having a volume of 10 cubic feet contains saturated water vapor at 212 degrees Fahrenheit. The water is rapidly stirred until the pressure is 20 pounds force per square inch. Determine the temperature at the final state in degrees Fahrenheit and the work during the process in BTU. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. Highlighted in red we have a well-insulated rigid tank having a volume of 10 cubic feet contains saturated water vapor at 212 degrees Fahrenheit. The water is rapidly stirred until the pressure is 20 pounds force per square inch. And highlighted in green we have determine the temperature at the final state in degrees Fahrenheit and the work during the process in BTU. Let's start to develop the solution. The first thing to do in any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in our critical read of the problem statement, presented here in a bulleted list format. By rapid stirring, water vapor in a well-insulated rigid tank is brought from the saturated vapor state at 212 degrees Fahrenheit to a pressure of 20 pounds force per square inch. The next thing to do is to summarize what we have to find. This is again the same information we highlighted in green in our critical read of the problem statement, presented again as a bulleted list. Determine the temperature at the final state and the work. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. Let's highlight a few important pieces of information that were provided to us, which will help develop our solution. The first thing to note is that there is no mass entering or leaving the tank. This immediately suggests that a closed system approach is the correct one. Having recognized this key fact, let's select our system boundary. In this case, it is selected to enclose the water and follow the physical boundary of the tank as shown on the schematic with a red dashed line. Also, the schematic clearly indicates that the working substance contained in the tank is water. Also, the shaft going through the boundary stirring the water. The next step is to develop, as requested, the appropriate thermodynamic diagram to represent the process. The first one shown on the left is the PV diagram. State 1 is saturated vapor at a given temperature and hence on the right edge of the vapor dome and at a pressure of 14.7 pounds force per square inch according to the saturation table for water. State 2 is at the given final pressure of 20 pounds force per square inch but at the same volume as the tank is rigid, hence along a vertical line on this PV diagram. Given the shape of the vapor dome, state 2 is in the superheated region to the right of the vapor dome and at a temperature T sub 2. Now, let's represent the process on the TV diagram as shown on the right. State 1, as saturated vapor, is also on the right edge of the vapor dome. As mentioned before, for the given temperature, the saturation pressure from the saturation table for water is 14.7 pounds force per square inch. State 2 is at the given pressure P sub 2 in the superheated region to the right of the vapor dome, and the process from 1 to 2 is along a constant volume line. While not explicitly requested in the problem statement, it is always a good practice to represent the process on appropriate thermodynamic diagrams to guide our analysis. The next step is to develop an engineering model, which is a set of simplifying assumptions which will allow us to perform the analysis of the problem. 1. The water is a closed system. 2. The initial and final states are at equilibrium. There is no net change in kinetic or potential energy. 3. There is no heat transfer with the surroundings as the tank is well insulated. Having completed all the required preliminary steps for our solution, let's develop our analysis. To determine the final equilibrium state, the value of two independent intensive properties are required. One of these is the pressure, P sub 2, equal to 20 pounds force per square inch, and the other is the specific volume, small v sub 2, equal to small v sub 1, as the mass is constant and the tank is rigid. As mentioned earlier, the initial and final specific volumes are equal because the total mass and the total volume are unchanged in the process. The initial and final states are located on the TV and PV diagrams presented before. From the table of properties of saturated water with a temperature index, small v sub 1 equals small v sub g at 212 degrees Fahrenheit, which is equal to 26.80 feet cubed per pound, and small u sub 1 equals to small u sub g at the same temperature of 212 degrees Fahrenheit and equal to 1077.6 BTU per pound. By using small v sub 2 equals to small v sub 1 and interpolating the table of superheated water vapor at a pressure P sub 2 equal to 20 pounds force per square inch, small u sub 2 equals to 1161.6 BTU per pound, and T sub 2 equals to 445 degrees Fahrenheit. This is the first answer we were seeking, the temperature of the water in the final state 2. Next, the energy balance for the closed system reduces to delta U plus delta KE plus delta PE equals Q minus W, where the crossed out terms cancel with assumptions 2 and 3. After rearranging the terms and solving for work W, we get W equals to minus U sub 2 minus U sub 1, which is equal to minus M times small u sub 2 minus small u sub 1. To evaluate the work W requires to determine the mass M. This can be determined from the volume of the tank and the specific volume. M equals to capital V divided by small v sub 1, and substituting the numerical values we get M equals to 0.373 pounds. Finally, by inserting numerical values into the expression for the work W, we get the following, giving us a value of W equal to minus 31.3 BTU. This is the second answer we were asked to determine, the work during the process from 1 to 2, where the minus sign signifies that the energy transfer by work is done to the system by the mechanical shaft driving the mixing paddle. To finish, I would like to make a few comments on the solution we just developed. Although the initial and final states are equilibrium states, the intervening states are not at equilibrium. To emphasize this, the process has been represented on the TV and PV diagrams by a dashed line. Solid lines on property diagrams are reserved for processes that pass through equilibrium states or quasi-equilibrium states. The analysis illustrates the importance of carefully sketching property diagrams to guide our problem solution. Also, the mechanical work input to the mixing paddle is transformed in this stirring process to heat, resulting in a temperature increase of the water in this well-insulated tank. Quick quiz. If the insulation were removed from the tank and the water cooled at constant volume from T sub 2 equals 445 degrees Fahrenheit to T sub 3 equals 300 degrees Fahrenheit while no stirring occurs, determine the heat transfer in BTU. You may want to stop the video at this point to solve the question. The answer is minus 19.5 BTU. If you had difficulties getting this answer, here are a few hints on how to proceed. From earlier analysis at T sub 2 equals to 445 degrees Fahrenheit and P sub 2 equals to 20 pounds force per square inch, we got small u sub 2 equals to 1,161.6 BTU per pound. At T sub 3 equals to 300 degrees Fahrenheit with V sub 3 equal to V sub 2, by interpolation in the table of superheated water vapor, we get small u sub 3 equals to 1,109 BTU per pound, also corresponding to a pressure of 16.7 pounds force per square inch. Next, in the absence of work from 2 to 3, the energy equation allows us to evaluate the heat transfer from 2 to 3 as Q equals m times small u sub 3 minus small u sub 2. Evaluating the expression numerically is left as an exercise. In closing, in this example, we have learned about analyzing the process of stirring water in a closed, rigid, and well-insulated tank. By applying the energy balance for this closed system, the process resulted in an increase in the temperature in the tank, and the work of stirring the water was evaluated. This concludes the step-by-step solution of the example entitled Stirring Water at Constant Volume.